Let's attempt to solve another problem in our study of the combined effect of translational equilibrium and rotational equilibrium. So here you see a pizza sign. This would be typical of the type of signage you see maybe on a kind of old-timey downtown Main Street storefront. So the sign hangs some distance, I don't know, we can just call it a distance of d from this hinge. And the pizza sign has a mass m. It hangs from a beam, and the beam itself has a mass, maybe we'll call it capital M. So there's a support cable that provides a counter torque to overcome the weight of both the beam and the sign. And that cable forms a tension member that makes an angle of theta with the beam. So we've got tension in a cable that provides some counterclockwise torque relative to an axis within the hinge, and both the mass of the sign and the beam itself create some clockwise torque, meaning the weights of both of these want to make it rotate in this direction. The tension helps make it rotate back this way. So the idea is that those torques have to cancel out so that the net torque is zero, and we satisfy the condition for rotational equilibrium. But then the question goes, what about the reaction force at the hinge? In what direction does the hinge push on this end of the beam? So it has to push a little bit outward because there's going to be a component of this tension vector. If the tension vector really does point at this angle theta, then we can break that tension vector into two components. There's a component to the left, and there's a component pointing up. Now, if we apply the other condition for equilibrium that says net force equals zero, then this vertical component of the tension offsets some of the weight of the pizza sign and some of the weight of the beam. But there's no guarantee that that component of tension exactly equals the sum of these two weights, because there could be some vertical component to the force at the hinge. There's certainly this horizontal component to help offset the horizontal component of the tension. Okay, so this is a two-part problem. First part, find how much tension is in this cable, and then the second part, find out the reaction force at the hinge. So let's continue. Here we've got it diagrammed a little bit better. We'll say that the length of the beam is 4 meters. The pizza sign has a mass of 12 kilograms. The beam has a mass of 5 kilograms. The angle is 30 degrees. And we've identified the center of mass of the beam. So the distance from the hinge to the place where the force of gravity, capital mg, is applied would be 2 meters. And then we have our lowercase mg at a distance of, we'll just call it d, and let's say d is 3 meters. Okay, so all those values are copied here. The sign is 12 kilograms, the beam is 5 kilograms, it's 4 meters long, angle of 30 degrees, and the sign hangs 3 meters from the hinge. So if we simplify the drawing a little bit so we can see it as a rigid body diagram, we can picture it like this. So we keep in mind that we're assuming the axis of rotation is in the center, although we could really put the axis anywhere we want, because if the net torque is equal to zero, then there's zero angular acceleration, and if the beam starts at rest, then it maintains zero angular speed. So no matter what axis you imagine, if you imagine the center of mass as the axis of rotation or the right end, there's no value of omega about any of these axes, so you're free to pick any axis you want. However, for the sake of this problem, we'll just agree to imagine the axis is in this hinge at the left side. So we'll start with the second condition for equilibrium that says net torque has to equal zero. So we need to consider clockwise torque and compare that to the counterclockwise torque. So clockwise torque comes from both the weight of the beam and the weight of the sign. And as always, we have to multiply a force times the lever arm times the sine of an angle, although the angle between the beam and the gravity vectors is 90 degrees. So we can calculate torque just by considering force and length of lever arm. So there's a torque due to the weight of the sine, force times lever arm of L over 2, plus the other force from the sine, mg, with a lever arm of D. Okay, and then the counterclockwise torque comes from the tension in the cable. So we have to multiply force, that's the tension, times a lever arm, that's the length of the entire beam. In this case, the angle is not 90 degrees, it's theta, so times sine theta. So for the net torque to equal 0, the clockwise and counterclockwise have to match in magnitude. So we have TL sine theta has to equal, let's factor out the g, has to equal g times the quantity capital ML over 2 plus lowercase md. So in other words, T is equal to G times capital ML over 2 plus lowercase md, all divided by L sine theta. So that's pretty good. Even if we didn't give any numerical values in this problem, we could at least solve it algebraically. If we want to plug in the given values, then the tension is equal to, we'll round up for G, call it 10 newtons per kilogram, multiplied by, what is this? Oh no, I'm sorry. 12 is the mass of the sine, isn't it? 5 times 4 divided by 2 plus 12 times 3. There we go. All divided by 4 times sine of 30 degrees. Oh, what is this? Kilograms and meters. And again, kilograms and meters. So the kilograms cancel out. And, oh, this 4 down here is in meters. So the meters cancel. So yeah, we're left with newtons. So the units work out. Numerically, we find that this tension is equal to 10 times, let's see, this would be 20 divided by 2, so that would be 10. 12 times 3 is 36. Sine of 30 is 1/2, so we have 2 in the denominator. So it looks like we've got 460 newtons divided by 2 gives us 230 newtons. Okay. So we solved question number 1. What's the tension in the cable? It's 230 newtons. Question number 2, what's the reaction force at the hinge? So from that, we'll take the first condition for equilibrium. The sum of all force has to equal 0. So again, we draw a rigid body diagram. There's the beam. Oop. There's our tension vector, and then we have our 2 gravity vectors. So if this is 5 kilograms, is going to be 5 times G is 10, right? So this is 50 newtons, and then this is 12. G will round up to 10, so that's 120 newtons. So we have a total downward force equal to 170 newtons. This tension we solved for, and we found it's 230 newtons. Well, that tension should be broken into components. So it has a component to the left, and it has a component pointing up. So this would be T times sine of 30 degrees, and this would be T cosine 30 degrees. Well, T sine 30 is the same thing as 1/2 of T, which would give us 115 newtons. So now wait a minute. There's 115 newtons of upward force, but there's 170 newtons of downward force. So there must be some other force acting back at the hinge to point up to account for the difference between the vertical component of the tension and the overall downward force of gravity. The difference between 170 and 115 is 55 newtons, so we at least know the vertical component to the reaction force at the hinge. The horizontal component, well, there's only one horizontal force that needs to be balanced out, and that's the horizontal component to the tension. So that means at the hinge there must be a force to the right, F subscript x, that's just as big as T cosine 30 degrees. So if you do 230 times the cosine of 30 degrees, your calculator should say that's 199 newtons. So overall, at the hinge, we have a force to the right of 199 newtons, a force in the vertical direction of 55 newtons, and so the overall reaction force points at some angle. Well, we already labeled this angle as theta, so let's pick a different Greek letter. We'll call it phi. And so let's figure out both F and phi so we can get the overall force from the Pythagorean theorem. So 55 squared plus 199 squared. And what do we get as the final answer? We get about 206 newtons. And for our angle, well, tangent is equal to opposite over adjacent. So the tangent of phi is 155 over, is 55 over 199. So we take the inverse tangent of that ratio and we find phi is about 15.4 degrees. So just one more example of applying the laws for equilibrium.